So now we are looking at objects that are moving in circles, right? We have seen what is angular displacement. What is the next idea? How fast is it turning? What would that be? Angular velocity. So we are going to study now the idea of angular velocity. How is linear velocity defined? It is defined as displacement by time. So if I want to look at the definition of linear velocity, usually I say displacement, which I write it as delta x, during a time interval delta t, right? So basically we say change in position by time, that is displacement by time. The same way angular velocity is defined as the angular displacement, which is delta theta, by the time interval. We write delta t because we want to say time interval. Sometimes you don't want to say delta t, you say the time itself is t, the time interval itself is t. Then you might write it as final angle minus initial angular position by the time. So this is fine. It makes a small assumption. The assumption is that this is uniform. It's not a small assumption, it's a big assumption. Okay, but we will make the assumption that this is uniform. Okay, so with that assumption, this is valid. Now, first let's try to understand this. What is this saying? This is saying the rate at which the angle is changing. Why am I saying rate? Because it's not just saying that there was a change of pi by 2 radians. It is saying pi by 2 radians in 2 seconds or pi by 2 radians in 10 seconds. If it was pi by 2 radians in 10 seconds, that means it was changing slowly. If it was pi by 2 radians in 2 seconds, that means it was changing fast. So this is actually measuring how quickly is the angle changing. So we call this angular velocity. Okay. If it is velocity, shouldn't it have direction? Yes, we will come to that in a minute. Right now, don't worry too much about whether it is speed or angular velocity. We'll think of it as angular speed can be defined this way, but we will use the word angular velocity. Now let us take the example of this. So suppose a particle goes from A to B. I don't even need to know the radius. I only need to know how much has the angle turned. Well, at this position A, its position was pi by 4, and at 60 degrees its position is pi by 3. So what is delta theta? Angular displacement. Pi by 3 minus pi by 4, which is pi by 12 radians. Suppose this whole thing, the turning took 3 seconds. It's very slow, right? It's turning slowly. So, but remember that it may not be turning really slowly because this radius may be huge. So the object is moving very fast. Angular velocity is low. So what would be the angular velocity? Delta theta by time 3. This is in radians, this is in seconds, and so this turns out to be pi by 36. Pi by 12, whole thing divided by 3 is pi by 36 radians per second. So this is the unit for angular velocity, radians per second. So because this is in radians, this is in seconds. Sometimes because radians is not mentioned, we might write pi by 36 second power minus 1, just simply per second. What per second? Nothing per second, because radians means nothing. Okay, but I don't like this, so therefore we'll use radians per second, just to clarify that you're talking about angles in radians per second. But sometimes you may just say per second, so sometimes this is also a good unit. We won't use it much, but if you see this unit, don't get confused, it just simply means radians per second. Okay, so that gives you the angular velocity, but this assumes that the angular velocity was uniform. Suppose it was non-uniform. Then what happens? Then you can't really use large angles like this. So then you have to say, okay, in the beginning the particle was there, in a very small amount of time, dt seconds, we use dt to say it's very tiny amount of time, it would have turned by a small tiny angle. Now just like I called that dt, this angle I will call it d theta. So angular velocity for this period, I am going to think of it as almost uniform. And the smaller you make the time, we can assume that it is uniform because the time interval is so small, it didn't have time to change. In that case, we can say angular velocity instantaneous is d theta by dt. So we call this instantaneous angular velocity at time t, at that time. So this time is t plus dt. So that is that way we will calculate angular velocity at any given instant. Then what about this? This happens to be average. So this I assumed was uniform, but suppose it was not uniform, we will use the same definition for average. So omega average, the way we will write it is omega with a bar on top. So this simply means average angular velocity is delta theta by delta t, or theta final minus theta initial by delta t. But when I write it in this form, I'll just write t. Okay, so this is the time interval t. So I hope this is clear. The definition of average angular velocity is delta theta by delta t. In case the omega was uniform, whether you're talking about average or you're talking about omega, it is the same. So therefore, for uniform, we can also write this as the definition for the omega. So we can basically say that this and this are the same if it is uniform, because then this basically becomes equal to omega. Okay, let us rewrite this, because the way we will think of it is we can always write average omega into time, the time interval is delta theta. I am now rewriting this delta t as t. So average angular velocity into time gives you the angular displacement always. Okay, so this is something that is always true. But if you look at omega into t, this is not always true. This is only true for uniform. That is always true. This is only true if it is uniform. If you wanted to write it for non-uniform case, d theta is omega times dt. Now that is also always true. Here what we are doing is we are starting with omega and finding angle. In this case we are starting with angle and finding omega. So that's the only difference. So I hope this is clear. Angular velocity is final minus initial angular position, which is angular displacement, divided by the time interval, gives you the average angular velocity. Instantaneous angular velocity would be d theta by dt. So I hope that is clear. Right. Now if a particle is moving in a uniform circular motion, we call this uniform circular motion. What is the definition of uniform circular motion? Because we'll use this a lot. What is uniform? What is uniform motion? Uniform motion means velocity is constant, not speed. If an object goes around like this, it is uniform speed, but it may not be uniform motion. Uniform motion means velocity must be constant. Uniform circular motion, velocity is not constant. Obviously the velocity was like that, then it is going like this, it is turning. What is constant? Well, we will talk about speed and we'll talk about uniform linear speed also. But what really is constant when it is going around is the angular velocity is uniform or constant. If angular velocity as it's going around is constant, we say the particle is going in uniform circular motion. Okay? Now if that happens, that means omega is constant, you can use this. Correct? How much angle would it have covered in capital T seconds when it comes back to this place? If it takes T seconds to come back to the same place, how much time? Let's say capital T. How much angle would it have covered? Omega t. But I already know it has come back, so that means that must be 2 pi. So we can write t equals 2 pi by omega. This t is called the time period. If it is going in a circle with uniform circular motion, then we can say that the time period of going around, if it starts here, it comes back to this place, the time period is 2 pi by omega. It doesn't have to start here, it starts here to come back to this place. Also the angular displacement, look at this, this is not angular position, displacement. So you start here and you come back, your angular displacement is 2 pi. 2 pi must be omega t. So t must be 2 pi by omega. So if time period is given, you can find omega. If omega is given, you can find time period. So that is very useful and important. Only works if it is uniform circular motion. But what is uniform here? Omega is uniform. Okay. Many times when we talk about angular velocity, we want to look at a direction. So how do we get that direction? So let me just quickly emphasize. If you are going in this direction, we define the angular velocity to be this way. That sounds a little weird. You are going like this in this plane of the board, but I'm defining the angular velocity to be pointing out of the board. Why does that work? Now, let's not worry too much about why it works. That's how it's defined. We will see later. It's a very brilliant definition. Okay, so this was something that a lot of people used, particularly Maxwell. So it's called Maxwell's right-hand thumb rule. You might have learnt it with magnetism. Let us come back to this. Use your right hand. You may be a right-handed person, left-handed person, doesn't matter. Here you have to use only the right hand. So take your right hand, curl your fingers along the direction in which the particle is moving, rotating. And then if this tells you the direction in which the rotation happens, your thumb points in the direction of omega. So if the object is going anti-clockwise, the direction is this way, right? So usually we put a dot and say that is the direction. But I like an axis system. This is called the x-axis, that is called the y-axis. So we use I cap and j cap for this, right? We use the thumb rule even here. So from x you go to y, your thumb points this way. So this direction is called the z-axis. I can't draw like this. I can't take an arrow and point it. Okay, you should think of it this way. So this is the direction. But I'm going to draw it like this and say that this is the z-axis. It just simply means that this is actually 3-dimensional. You have to imagine the 3-dimensional case. The z-axis coming out direction is called k cap. So we will write that if it goes like this, anti-clockwise, it is k cap, omega in the k cap direction. If it is going in the other way like this, look at my thumb, it's pointing in, so that would be minus k cap. So if I tell you that an object has 3 radians per second k cap, so 3 k cap radians per second, is it going clockwise or anti-clockwise on the board? Well, 3 k cap means it's pointing like this, which means it must be going anti-clockwise. And if I had said it was minus 3 k cap, that means it is pointing inwards, right? Because that is the k cap. This is the k cap, that is minus k cap. So minus 3 k cap means it is going clockwise. So if this is going clockwise, this is this way. If it was plus 3, it would be going that way. So we will keep using this idea that angular velocity is a velocity, so it is a vector. So is angular vector? No. Small angles happen to be vectors. We will later learn that d theta is a vector, omega is a vector, but theta, delta theta and all are not really vectors. It's a little weird, I know, but don't worry too much about it. But angular velocity is a vector, so that's all I want you to know. Angular velocity is a vector, and the way the vector is designed is that if it's going this way, using your right hand, the thumb points the direction of the angular velocity. If you're going like this, you're not in the board, you are in the perpendicular plane like this, let us say. So that z-axis, y-axis. So if you're in the zy plane, then this is my direction. Remember, that was the x-axis direction. So this would be omega in the minus I cap direction. So you'll have to think about that and then apply it. We won't use too much of this, so nothing much to worry. Just remember that sometimes you may be given, instead of being given, it is going clockwise or anti-clockwise. Somebody may say, hey, omega is 5 pi k cap radians per second. So what are they saying? In a complicated, messy way, they are now telling you that the object is going in the anti-clockwise direction because omega is pointing this way. Okay? Because omega is saying k cap is that direction. So it is going in the anti-clockwise if I think of it in terms of the board. So that's all. That's the only reason you need to know this. So overall, I hope the idea of angular velocity is clear. Remember, angular velocity is d theta by dt if theta is not changing uniformly. If angular velocity is not constant, you have to use d theta by dt. Otherwise, delta theta by delta t will only give you the average value of the angular velocity. And for doing this, you need the stuff that we have learned earlier. That is, if you go around and come back, you don't become zero. Because otherwise, imagine that I came like this and I just crossed over. I would have got 0 and here I would have been 2 pi. I would have made a small angle change, but my angle change would have been from 2 pi to 0, which would be a big change. To avoid that is why we started off by saying when you continue, it has to be continuous. When you go around like this, it has to be continuous. So if you consistently use that, you will find that angular velocity will be nice and simple matter to calculate. Let us look at this example. In the first one, a particle is moving in uniform circular motion. The fact that it says uniform means that angular velocity is constant. It covers 15 degrees. I don't know where it starts, but it covers 15 degrees in a time of 5 seconds. Now, if I want the omega, you can write it as 15 degrees by 5 seconds and write this whole thing as 3 degrees per second. Though technically correct, this is not the way people are going to accept your answer. So you need to convert everything to radians. So this is okay, but we will not write it this way. So instead we will write 15 degrees is pi by 6 is 30, so by 2, so pi by 12 radians. So it covers pi by 12, so delta theta by the time delta t, average velocity, but this average velocity is now the same as instantaneous velocity because it is uniform. So if you look at the velocity, delta theta by delta t, what do we get? We get pi by 12 divided by 5. Okay, this is in radians, this is in seconds. And so it is pi by 60 radians per second. So this is the angular velocity, instantaneous angular velocity, and of course because it's uniform, you can think of it also as average angular velocity. So I hope that is clear. Now let us go to the second question that is asked. The theta is given, it is 4 plus 7t plus 11t square. Okay, we want to find omega at t equals 0 and omega at t equals 10 seconds. What is omega at t equals 0? Let's calculate. Omega in general is d theta by dt. This is omega at time t. This is the instantaneous. Whenever somebody asks you like this, it means instantaneous angular velocity. So what is the instantaneous angular velocity? Well, I need to differentiate theta. When if I differentiate theta, differentiate 4, you will end up with 0. Differentiate 7t with respect to t, you get 7 into differentiate t is 1 of course, plus 11 times differentiation of t square, which is 2t. So it is 7 plus 22t radians per second. This is at any given time t, this is the angular velocity. Now I want angular velocity at time 0, so substitute t equals 0. So you get 7 radians per second. By the way, it's very fast. 7 radians in 1 second is a lot of, it's almost completing one full loop within a second. 2 pi is 6 point something, right? 6.28. That means you have completed a full loop. This is 7, which is faster than 2 pi. Okay. And what is the omega at t equals 10 seconds? Well, substitute 10. So that is going to make this 7 plus 22 into 10. So 227 radians per second. That is super fast. Like this is really, really high. Okay, so this gives me instantaneous angular velocity at t equals 0, instantaneous angular velocity at t equals 10 seconds, and that's what is asked. But suppose somebody says, no, I don't want this. I want the average angular velocity during the first 10 seconds. You can't calculate it like this. Remember, average angular velocity is delta theta by delta t. In this case, it is 10 seconds. So this is easy. But what is the delta theta? Theta in the beginning, theta in the end. These are the two things that we need to calculate. What is theta at t equals 0? Substitute 0. It is 4 radians. I am not writing radians. Okay. And then what is theta final, which is theta at 10 seconds? Substitute 10. So you will end up with 4 plus 70 plus 100 like 11 into 100. So 1100. Right? So if I add this, I'm going to end up with 1174 radians. So if I look at delta theta, it is 1174 minus 4. So 1170, right, radians. So if I divide the two, I'm going to get 117 radians per second. This is the average angular velocity during the first 10 seconds. If I try to do this plus that by 2, will I get this? We may not. That depends on whether this was uniform angular velocity or not. In this case, actually it will turn out to be, okay, that it has uniform angular acceleration. We will later learn that if it's uniform angular acceleration, you can take this, do that and add and divide by 2. So if I did 7 plus 227 by 2, this is going to give me, this is going to give me 117. You can do the calculation, you will see that it's going to be 117. So it just turns out that these two are equal. This is the wrong way to do it in general. If I had not given you t square but I had given you t cube, you will find that it won't work. Okay, this will be always valid because you can do d theta by dt, and it's always true that average angular velocity is the total change in the angle, which is angular displacement divided by the time. Angular displacement, this is how you calculate, it's 1170 radians by the time 10 seconds gives me 117. So you know hopefully how to calculate average angular velocity, instantaneous angular velocity. Sometimes it may turn out that you can use initial plus final by 2 to find the average angular velocity. Don't use it. Use it only when you know. It turns out that like we have for linear velocities, when it is uniformly accelerated, the same way we'll talk about uniform angular acceleration. When you have uniform angular acceleration, you can use something of that sort. But don't worry about it right now. D theta by dt when the angle is changing non-uniformly, which basically means it's not uniform circular motion. You can use this to calculate instantaneous velocity, if angular velocity, if it was uniform. That's what I did here. Here I just did d theta by dt, or delta theta by delta t. This works to calculate instantaneous velocity, angular velocity, because it was uniform. If it is not uniform, use d theta by dt. Let us now look at a simple example. So in this, a particle has an angular velocity of pi k cap. What does that mean, pi k cap? K cap is this way, right? So the particle is moving in which direction? If it is angular velocity in this direction, it is moving like this. So it means that it has an angular velocity in the anti-clockwise direction. And the angular velocity is pi radians per second. Okay, so if this is what it is doing, I want to know the time it takes to go from A to B. Now A is here and B was there. But if it is going in this direction to go from A to B, it is going to go like this. How much time will it take? The time it will take into omega must be equal to delta theta, right? Angular displacement. But what is the angular displacement from A to B? Let's think about that. 45 degrees, that is 90 degrees. So this angle, this is delta theta. So delta theta is how much? 3 pi by 2. Why 3 pi by 2? Because this is 90 degrees, 4 90s make a 360. So this must be 3 90s, right? So 3 90s is 3 times pi by 2. So 3 pi by 2. And plus direction, because it's in this direction. So this is 3 pi by 2. And so t is 3 pi by 2 divided by pi. And therefore the time is 1.5 seconds. So it takes 1.5 seconds. So this is the answer to the first part. If omega was pi k cap, that is it was going this way, it would have taken 1.5 seconds to go from A to B. But if omega is minus pi k cap, so for the second part, which way is it going? If it is minus pi, that means it is this way. And so that means omega is pointing in this direction. So now it is going like this clockwise, right? And it is starting at A and it is going to B. So how much would its angular displacement be? Delta theta, how much is it? It is 90 degrees like this, which is minus pi by 2 radians. Right? This must be omega, which is, if I wanted to call that as plus, I should have called this as minus pi. Okay, so minus pi into t. Or you can just simply say, well, it's turning this much, pi by 2, divided by the angular speed, which is pi. So you can write pi by 2 by pi, half a second, 0.5 seconds. Notice that when it is going like this, it is 0.5 seconds. When it is going like that, it is 1.5 seconds. It does matter. The time clearly is very different. It must matter whether it was pi k cap or minus pi k cap. Pi k cap means the angular velocity is like that. Minus pi k cap means the angular velocity is like this. So I hope that is clear.